now we're going to ramp down this understanding of this experimental data. We've explained how strain and quantum dot shape are important. Now you can ask yourself, well, how solid are your assumptions against experimental variations that you know nothing about, right? Because we assume some nice quantum dot that's nicely shaped, right? Is that important? Would we come to the same conclusions if we assumed something else? So let's do a couple of different assumptions. So one is that the interface, you can certainly be guaranteed, is not going to be exactly well defined. In fact, there could be interface diffusion, or there could be a gradient on this interface. So what we do is we make sort of 3 shells, and we have different indium concentrations in each shell. So in the core, in the ideal case, we would have 20 nanometer of x1 equal x2 equal x3, where x is just 1, meaning just pure indium. But then we can relax the indium concentration in these outer shells to sort of mimic how interface interdiffusion could change this thing. All right, so we start with the ideal case that we had shown before of x1 equal x2 equal x3 of 1, 1, 1, right? And then we make it 1.9.8 and 1.7.6. So it's really getting more and more indium gallium arsenide-like, so we soften the interface, assuming that there is an interface interdiffusion, that at the growth process, it's not a perfect interface. So what happens? If you do that in these 3 cases, basically you sort of lower the optical line width a little bit. So you go from the red line to the blue line to the green line, but the shape of the lines doesn't change a whole lot. So the nonlinearity doesn't change, and we're not out of the ballpark. It's not like suddenly the whole optical emission would look rather different. Okay, it's a pretty smooth effect. It doesn't radically change our conclusions. All right. So the conclusion here is if we change the interface slightly, it's not going to change things dramatically. So the next thing you can say is, well, but you don't know what the size of these dots are exactly. Would you come to the same conclusions if the dot size would change? So normally we had assumed a diameter of 20 and a height of 5 nanometers. So we're going to do a case where we raise the base size to 21 nanometers and the height to 5.5 nanometers. And what we see here is in these 2 cases, red was the previous case we had all along. If we make the height, the diameter larger to 21, we get a small increase. And if we make the height bigger, we get a much larger increase. Which also makes sense, because the height is the critical dimension of our particle, right? Particle in a box problem. The lateral direction is weak, has a weaker influence, just like with this aspect ratio. So that makes sense. But the bottom line is, again, the nonlinearity remains, and it's a smooth effect. It doesn't change our fundamental conclusions about this experiment. So overall, these device characteristics are relatively insensitive towards experimental imperfections, and there's small wavelength changes and the same nonlinearities. Okay? We didn't just hit a lucky spot where we matched the experiment, but ballpark, you would come to the same conclusions even if you had small variations in height and base width or interface details. Okay. The last point I want to drive home is that there are some papers out there that try to explain the very same data by saying that having a buffer layer around it, this indium gallium arsenide buffer layer around it, changes the confinement of the electrons and the holes because it effectively lowers the barrier. And the point here we want to do is that that is not the case. That confinement is not the critical element here, but it's the strain and or let me put it this way, that leakage of the wave function in the buffer is not the critical element. And we sort of prove that by, instead of having indium gallium arsenide around as a buffer, we take indium aluminum arsenide, which has a much larger band gap, but roughly the same strain behavior. And we basically get the same points that we had computed before. So we get the same results. These are the green stars here. All right. So the single band model would have predicted that there's a redshift of the emission spectra due to a reduced confinement. And in our numerical experiment, we introduce a material as a buffer that has a larger gap, so it should repel the electrons to be closer in the dot if leakage were a problem, and we get the same result, basically. That means the change in confinement on the wave function is not a significant effect, and really the continuum model also in this case, as I had shown in previous lectures, can lead to the wrong conclusion. What that model doesn't have is the bimodal distribution of the indium arsenide, gallium arsenide, and it doesn't have the atomistic representation of the strain, and therefore comes to the wrong conclusion. So, in summary, what we were able to do is, through modeling of a large structure that has strain built into it and has atomistic electronic structure, we can basically have quantitative agreement with experimental data. We studied the sensitivity to experimental imperfections. We find small variations of our conclusions against these imperfections, and that effective mass theories provide the wrong guidance to explain what comes in this experiment. Right? Clear as mud? Any questions? Okay. All right, so I'm going to move on to the next presentation. We have half an hour before we...
30 minutes.
How much?
1-3.
1-3, okay.